last lecture on electricity, day 23. Yes, it also says magnetism. Normally we get to magnetism. Unfortunately, that's probably not clearly going to happen. So it's really just electricity that you kind of did in the lab. This is about the only lab that you're able to do online that's somewhat inquiry, although there was a major mistake in it that I will get to here in a little bit. So, anywho, yes. Electrical basics. Couple things you need to know. Charge will indicate the presence of ions. If you remember from your chemistry class, you have your positive ions, your positive cations, and your negative anions, and things like that. Well, a charge indicates that there are ions somewhere present. Um, a continuous loop of electrical devices that allows charge to flow, that's called a circuit. Normally, ooh, that was really ugly. Normally, when we draw circuits, um, it's kind of beyond the scope of this class, but you would have some sort of battery attached to some sort of object, such as a light bulb, and then charge will flow from one direction. It is said that charge will flow from positive to negative. In the lab, I pointed out that the electrons actually drift backwards in the opposite direction um, because, what are electrons attracted to? Positive things. And if this is truly a positive end over here, electrons should be attracted to it. They don't move very fast. The simulations that you see are charge, and charge is different than the electrons actually moving. The best, I guess you can call it an analogy, that I can think of is it's kind of like dominoes, except all the dominoes are rigid at the bottom. So if you had, let's say your dominoes are really flexible. Let's say they're all made out of rubber, rubber, and these, that's a really bad one. And basically what happens is charge can kind of flow and be passed off from piece to piece. That's the best analogy I can think of. The electrons themselves aren't really moving and they don't move very fast. It's more the charge that is moving. And so we say it flows from positive to negative. That's just kind of the convention. We've talked about this with respect to heat, but with electricity, there are things called conductors and insulators. Conductors will allow charge to flow. Those are mostly metals, which will allow charge to flow. Tap water would be a conductor. Why tap water? Because tap water has the ions in it that can carry the charge. So there's that. And then distilled water is more of an insulator. Insulators are your rubbers or your ceramics. Those are insulators. Now, you can run a charge through anything you want. Well, as far as I know. You can run a charge in through rubber all the same. It's just it takes a lot more potential, electrical potential, to do it. And so that's why it's not really, like, rubber's not completely safe. It's just a insulator. It insulates you. It impedes the flow of charge. So there's that. And lastly, you have charge by induction and charge by conduction. A little bit of semantics, but induction you can think of is it doesn't actually touch. And so this was when John Travoltage gets close to the doorknob, yet the charge still dispels. That's more by charge by induction. Conduction, just like with regular conductors or any type of regular conduction through heat, actually flows through material. So, yeah, those are your kind of your two types of conduction and induction. Current magnetism. Current is the flow rate of charge, and this is measured in amps. And as I mentioned this earlier, a charge unit, like much earlier, is a C, which is known as a coulomb. I believe I spelled that correctly. I'm not good at my spelling. That's the unit of charge, and an ampere is a coulomb per second. So it's telling you how much charge is flowing per second. And we did that when we dealt with amperes and voltage with the power supplies, albeit virtual power supplies. There's that. Finally, electrical currents will induce a magnetic field. And alternatively, a magnet moving through a conductor will create a electricity. So anytime you have moving electrical currents, it will create a magnetic field. And then if you move a magnet through a conductor, you will have electricity. So your basic, very, very basic way to have electricity is, let's say you have some coils. Oh wow, that's really bad. Let's say you have a coil of wire, and then you have some sort of magnet in between it. Basically you can rotate this coil around the magnet, and it will create a electricity. So anytime you have a magnet moving through a conductor, or vice versa, you can create electricity. That's kind of the basis. My drawing really sucks, by the way. Sorry. Of how to create electricity. So usually we talk about it with respect to compasses, but there wasn't a way to work that in that I could tell. Electric potential. We've kind of talked about this before. Electric potential is the measure of the potential for electricity to flow. That was when we had the volts. It's oftentimes people say that electric potential is the energy. It's not. It's the energy per unit charge, not just the energy. So voltage is joules per coulomb. And that basically says how much potential does it have to flow. The more volts, the more charge that can flow. So in most of the things that you see these are batteries. And generally your higher voltage batteries are generally more dangerous because it has more charge that flows. More potential for the charge that flows. Sorry. So that's your electric potential. Resistance. So on the PHET simulation, I had you put in resistors. They are a measure of electrical impedance of the object. So if you rip apart any type of, let's say, calculator or anything, you will find these little guys in here. These are resistors. The purpose of a resistor is that, let's say you've got a circuit. Let me draw one out here. Oh, that's really bad. I have not drawn a circuit with this before, so bear with me. And let's say it's hooked up to a light bulb. And let's say you've got, a 12 volt battery and a tiny light bulb. That 12 volt battery is going to blast away that light bulb and destroy it. So how do you light the light bulb? Put in a resistor. If you put in the appropriate resistor, it'll slow down the flow of charge so that the light bulb will still light without overwhelming it or breaking it. So that's kind of the function of the resistors. You might be thinking to yourself, well, it only works, it's a static resistor, it's not going to change. That's true. But they do have variable resistors out there that will change the resistance based off of like a switch or some type of dial. Like your radio or your volume control. That's basically a variable resistor. When you turn your volume up, like let's say on your car radio, what you're actually doing is you're lowering the resistance in the circuit, especially if it's an AC circuit. And I chose the car, or not AC, DC circuit. And I chose the car because I believe it is a DC circuit, or at least most are. So, to my knowledge, I'm not a big car guy. So, yeah, that's kind of what a resistor is, at least in that regard. My note to, I think I have one more. No, I have one more after this. It's measured in ohms. It's a very, very strange unit, but yes, it's measured in ohms. And all wires and bulbs have their own small internal resistance, as I kind of showed you, hopefully showed you in the little PHE simulation lab. So light bulbs have their very small resistance, as do wires. So the longer the wire, the more resistance that you're going to have. So erase that. All right, this is where I need to kind of clear up my mistake that I made. I accidentally, I had this made previously, or maybe I made that one recently. Basically I gave you kind of the wrong drawing on one of your problems. I put a resistor in the main circuit, and I needed to put it in parallel. But basically put on one of them, it comes to an incorrect assumption. I'll get there in a second. But we do have two things. We have a series and we have a parallel circuit. Your series circuits takes actually one path, and that's this one. and your parallel can have multiple paths. So, on my PHE simulation, I attempted to show that with resistors on a parallel path, as you add more resistors, the current actually drops. So more resistors. Sorry, I said it wrong. Current actually increases. More resistors. The resistance actually, overall resistance drops, but your overall current, will increase. And I set it up in a way that didn't quite work out, or at all rather. And I also made a discovery that even if I did do it right, it still didn't work. So I had to really look it up again. I'm like, okay, am I wrong on this? I believe it was actually kind of an issue with the way the simulation was set up, but it did scare me for a bit. I'm like, oh my god, I've been wrong all my life? No, not at least on this. So yeah, your overall current is going to increase as the more resistors you put in there. It's a little bit beyond the scope of this class. If you take Physics 2, 214 or 314, you go over it. But yeah, it's just kind of something to know. So parallel there's a lot, I'm generalizing right here, but with a parallel circuit and you put resistors in a parallel circuit, you can actually have more current, which kind of seems counterintuitive, but basically each time you're putting in a new resistor and a new pathway, you're giving the electricity another way of flowing. So yeah. For your test, since I or for the finals, when you'll see this, since I screwed at least this part up, I do expect you to know the difference between a series and a parallel circuit. Parallel has multiple ways of going, and series has one way of going. That's really the gist of what you need to get from the electricity part, at least the pandemic electricity section that I created. Okay, so this is on a Wednesday. Sorry I posted this a little bit later than normal. I actually thought I had done this already, and then I saw the mistake, and I'm like, crap, and then I fell behind, so yeah, sorry. Your Monday, you're going to have a test. It's going to be on Blackboard. I haven't decided what I'm going to do about your final. It may or may not be take-home. It may be on Blackboard. Currently, it's set up on Blackboard, but I'm just going to kind of see how this goes. So if you have problems on the test, please tell me. It's brand new. I have an idea of what I'm doing, but I can have a great idea of what I'm doing, and most of you are going to go on to teach at some point, and you can realize that, oh, you got everything planned out. No, you don't. No, you don't. There are so many unknown unknowns that you don't know that you even needed to know that to begin with. So I'm counting on a lot of unknown unknowns, or at least banking that there'll be some. So if you see any of those unknown unknowns, please let me know. Anyways, all right, that's it.